Hello, it's been a little while since I've made one of these, but now that we're into ray diagrams, I thought you'd find it really helpful. This purple dot over here, I'm actually on a different computer than I've normally used. This is a different machine, so a few things are different. Did I say different enough? Hopefully you find that helpful. So what we're going to be doing is we're going to be drawing ray diagrams for spherical mirrors. So a spherical mirror can curve this way. So if the light source, if this is the object over here, usually there'll be some distance of the object away, this would be considered concave, or what's known as a converging mirror, and this would be considered what is known as convex, or a diverging mirror. So this would again would be convex, this would be concave. First, I'll talk about the tracing rules for drawing rays. We're going to draw ray diagrams to scale. There are going to be some important things to understand about sign conventions. I'll go over the equations, and then we'll go through 4 cases. We'll go through concave when you're really far away, concave when you're sort of far away, and concave when you're really close, like closer than the focal length. And then finally, we'll look at convex. To help us understand that, I've got a simulation here that I've found online. You can Google this or go directly to this link and you can view that simulation. And today we're going to be looking at mirrors. So one of the first things you need to understand is that for a mirror, if it's curving towards the object, in other words, if it is concave, it's going to have a positive focal length. That's a convention that's going to be important. If it curves away, it's going to be what's known as convex. So I'll just show you briefly the cases we're going to look at are when you're further away than the radius of curvature, in between the focal length and the radius of curvature, and what happens when you are closer than the focal length. Now, first of all, spherical mirrors, what they do is if they take in rays of light that are parallel, now strictly speaking, only rays that are close to the optical axis here, those are going to come in parallel and they're going to go through the focal length. That's going to be one of our rules. Strictly speaking, that's only for parabolic mirrors, but when the light is close to this axis, we can assume that. The radius of curvature, if I was to actually draw a line from here to here and trace out a circle, clearly this isn't drawn to scale, what you would find is this being the radius and this being the curve of the circle. When the radius meets the outside of the circle, by definition the radius is perpendicular 90 degrees to that, and the ray would reflect straight back. And it turns out that it's always true that the focal length for a spherical mirror is 1/2 of the radius of curvature. So this distance is always going to be half of that for a mirror. That's going to be really important. So again, we're going to start off looking at a case when it's out here. Then we're going to look at a case somewhere in here. Then we're going to see what happens here. You can see there's a big change right at the focal length. We're going to explain what that is. So we'll probably come back to that simulation. But let's talk about the rules for convex and concave. I've already mentioned that for a concave mirror, one that's curved in, it's going to have a positive focal length. For a convex mirror, one that's bent the opposite way, that's going to be a negative focal length. This is the kind of mirror, if you've ever tried to steal things from a store, which I hope you haven't, this would most likely be the one they saw you stealing. The distance to the object, so if this is the object distance that's emitting light or reflecting light, if this is the object side of it, a positive object, or image distance rather, would be right here. So for an image distance, if it's in front of the mirror, in other words, on the same side of the mirror as the object, that's going to be considered a positive image distance. If, however, if this is the object and this is the image, if it's on the opposite side of the mirror as the object, that is considered a negative distance, and this is considered a virtual image. So images that are on the opposite side of the mirror than the object are considered virtual, and they're going to have a negative distance. So again, image distances that are positive are on the same side of the mirror as the object. They're real, and they're in front of the mirror. Virtual images form behind the mirror. It's got a negative image distance. And as I mentioned before, the radius of curvature, so if you've got and I'll exaggerate, a mirror like this that is spherical in nature, this is going to be the radius of curvature. If light rays come in parallel, at least close to the primary optical axis, they're all going to focus at a distance that is 1/2 of that, and that will be the focal length. So those are some information we need to get out of the way before we try to draw any of these diagrams. Now, these will make more sense as we actually go through them, but there are 3 rays that we're going to be drawing, and that's a ray parallel to the axis, to the optic axis. We're going to draw a treif ray, which is a ray that's drawn through the center of curvature, and then we're going to draw a focal ray. So parallel to the optical axis reflects through the focal point. That'll make more sense when we draw it. A treif ray, if you draw it through the center of curvature, reflects back along the same path. And a focal ray, if you draw it through the focus on the first side, it's going to reflect back parallel to the optics axis. And this fourth one we're not going to draw, only because it's, a little tougher to draw, is that if you have a mirror like this, or frankly like this, if you get it exactly at the center along the primary axis, it will always reflect back at the angle that it came in at, just like a plane mirror. But that's a little tougher to draw, so we're not going to be drawing that one. The equations that you want to know, for the image position, it's always going to be true that 1 over the focal length is equal to 1 over the distance to the object plus 1 over the distance to the image. Sign conventions are important here. Remember, an image that's on the same side as the object will be positive, and an image that's on the opposite side will be negative. Focal lengths for concave mirrors are going to be positive, and focal lengths for convex mirrors are going to be negative. Sorry for the interruption. And the magnification technically is a ratio of the height of the image over the height of the object. But practically speaking, it's often easier to get it as negative, the ratio of the image distance over the object distance. And this can be gotten by similar triangles, and I could derive that, but I think the video is probably long enough. So let's move on here. The first case I want to look at is far away. So what we're going to do is we're going to assume that this mirror, which is going to be concave, is going to have a focal length that's going to be plus 3 units. Doesn't really matter, centimeters, meters, little blue boxes, plus 3 little blue boxes. And we're going to place the object distance for this one at a distance of plus 9 units. And we're going to draw the ray diagram. We're going to see what that looks like. So what I'm going to do is I'm going to put on some axes, give us sort of a perspective here. And like that. And I should point out that I'll draw a little lens here, but you have to understand that we really are going to the center line. So if I draw this mirror, let me try to draw it like this. But you're really going to this red line every time. It's a good idea to label the focal length. So that's going to be 3 units away. And the radius of curvature, if you recall, is 6 units away, or twice that. In fact, let me make this curve the other way. Just people are more used to seeing it this way. So again, 1, 2, 3 is the focal length. 1, 2, 3 is the radius of curvature. And we need to put an image in at a position that is going to be 9 away. And let's make that a height of 4 boxes. If you want to play along, take out some graph paper. It's really a lot of fun. So we have 3 rules that we're going to use. Let me do it in blue. Blue's a good color. I like blue. And the parallel ray is going to go to that plane here, representing the center of the mirror. And if it comes in parallel, it's going to reflect through the focal point. So it's going to reflect like that. Now, you can also draw a ray through the center of curvature. Or the chief ray. So if I go like that. Now technically that defines a point right here where the image is going to form, but let's go ahead and let's draw the one other kind of ray we can have, which is to come through the focal point. And if it goes through the focal point, when it hits the mirror, it's going to reflect back in a direction that is parallel. So then that's going to give us an image here that looks like that. So let's see how we did. Let's use our theoretical or analytical equations. Now, 1 over the focal length equals 1 over the distance to the object plus 1 over the distance to the image. A fun little trick, at least I find it fun. Just as an aside, those of you who have me in class have seen me do this before. If I wanted to add 1/3 plus 2/7, some strange fraction, a lot of you guys have learned something about common denominators. I'm going to show you a trick. That trick is that if you multiply diagonally, 7 times 1 gives you 7, 3 times 2 gives you 6, 7 plus 6 gives you 13, and 3 times 7 gives you 21. That's a cool way to add. Well, you can apply that here, because that's going to mean that DO times 1, whoops, that's a typo, DO times 1 plus DI times 1 over DO DI equals 1 over F, or we could say that F equals DO DI over DO plus DI. And in the other ones, I'll probably jump right to this version of the equation. If we go ahead and we plug in the numbers, the DO is, again, 9. The DI is, well, we're looking for DI, so hold on, let me rearrange this equation. I'm falling asleep at the wheel here.